Thank you very much. So I think without further ado, we'll go straight into the lecture. So it's very kind, but very great pleasure to introduce Clare Dobbs, who is a professor of astrophysics at the University of Exeter, who's going to tell us about spiral galaxies, in particular M51, a good case study of M51. So Clare, over to you. Thank you. Nice to meet you.
Okay, yeah, thank you. Yeah, so hopefully you can see my slides.
We can, thank you.
Yep, so sorry, there's a sort of problem with the sound. Oh, it's fine now. It's been sorted. Yeah, so I do numerical simulations. I started doing these during my PhD. So I do simulations of galaxies and molecular clouds, which are star-forming regions. And my main interest, I'd say, is star formation, but I've also worked on looking at galactic structure. So these are sort of hydrodynamical simulations. They include gas. They can include stars as well. So if you're modeling a galaxy, you might include stars and gas. The dark matter halo is often just assumed as a potential, but you could model the halo live as well. That means sort of using particles to represent dark matter. So that's my background. I think I was asked to give a talk as there was some interest in what produces spiral arms in galaxies. And in particular, I produced simulations to reproduce the M51 or Whirlpool Galaxy. So what I've done is I've sort of spent half my talk talking about galactic structure and half on some sort of recent work that we're doing on star formation in galaxies. Sort of on galactic structure, just to introduce, you may well have seen this figure lots of times before, I don't know, but the galaxies were classified by Hubble into this tuning fork diagram. So we have like elliptical galaxies, which are just stars. They have little or no gas. And then we have spiral galaxies. So the ellipticals are sort of classed as according to their shape. So whether they're spheroidal or elongated. And then we have two branches with the spirals. We have barred spirals on the bottom and then unbarred spirals on the top. And they move from left to right according to the spiral arms. So they're more tightly wound on the left and more open on the right. So some sort of more modern versions of this diagram include other types of galaxies, only regular galaxies, but this is just more in keeping with the original one that Hubble did. So we have some ideas about how different galaxies are produced. So ellipticals, we nowadays think that ellipticals are often produced by galaxy mergers. So we think that the Milky Way will eventually merge with Andromeda, which will produce an elliptical galaxy. They may have formed when galaxies first formed. So then the difference between forming a spiral versus an elliptical will be related to the amount of angular momentum or rotation when the galaxy is initially forming. And then spiral galaxies, so these are all disk galaxies. Yeah, so a big topic is what produces the different types of structure. So I'm not going to talk anything about elliptical, but just focus on spirals. So then the second part of my talk is sort of the other big reason why we're interested in spiral arms, which is that they're sites of star formation. So this is a sort of a fairly busy poster that was put together by a Japanese group of astronomers that work in this area. And it shows three galaxies, so an artist's impression of the Milky Way, the M33 Triangulum Galaxy and Antennae Galaxy, and they've taken and they sort of highlighted little regions where star formation is occurring. The blue panels are showing molecular clouds. So stars in galaxies, they contain gas, and where this gas becomes dense and collapses due to gravity, that's where stars form. And this dense gas is molecular, so observed in CO, so-called molecular clouds. As you see, these molecular clouds are quite small compared with the sizes of the galaxies. And then in the optical images on the right, you can see some clusters that are associated with these molecular clouds. So this is sort of like what we observe in galaxies, and we tend to find that these molecular clouds and the clusters within them are often associated with spiral arms. So obviously the Milky Way is a sort of spiral galaxy, and M33. Antennae is actually two merging galaxies. So when you get merging galaxies, like we're saying that these produced an elliptical galaxy, you get a lot of star formation, and this may use up gas, so you end up with an elliptical galaxy that just mostly contains stars. Yeah, so going back to spiral structure and why galaxies have spiral arms, or why do disk galaxies have spiral arms? And quite a kind of simple answer to that is it's due to gravity and rotation. So it's actually quite easy to produce spiral structure in disk galaxies, but the problem is explaining the observed spiral patterns that we see in galaxies. So it's quite easy to produce some spiral patterns in disks, but not necessarily explain all of the diversity that we see across galaxies. So I'll start with the rotation. So this has two main types of rotation. So you can get solid body rotation. And when we kind of think about rotation ordinarily, we typically mean solid body rotation. So you could imagine in this picture that it's, say, a plate, and you draw a line from the center to the edge of the plate. If you rotate the plate by 180 degrees or any angle, then the line that you've drawn will just be exactly the same. I mean, it will be rotated, but you'll still get a straight line. But this isn't how galaxies rotate. And so instead, galaxies, and indeed stars like the sun, exhibit differential rotation. So if we draw our line again, and we rotate the star at A by 180 degrees, or half an orbit, then the other stars at B, C, and D won't have rotated as much, because with differential rotation, the galaxy rotates faster at the center compared with at larger radii. So this naturally leads to spiral features. So if you've got any sort of density perturbation in your galaxy that sort of spans some distance in radius, then this will be sheared out into a spiral. The other thing that we need to get spiral arms in galaxies is some sort of perturbation. So if you've got a completely smooth stellar disk, you won't get any spiral arms. But typically we think that galaxies are gravitationally unstable. And this was parameterized by Toomey in 1964, who developed something called a Q parameter, which determines whether a galactic disk is stable or unstable. And it depends on three parameters. So the velocity dispersion is just a measure of the random motions of the stars. Epicyclic frequency is sort of to do with the shear of the disk. And it also depends on the surface density. So that just depends on the mass in the disk, basically. So this is developed for stars and gas, just as slightly different numerical parameter for gas. And if Q is less than 1, and you can see that if the surface density higher, that makes Q smaller, then the disk is predicted to become unstable due to gravity. So in which case you can get if you get like an overdensity in the stars, then if it's unstable, that overdensity will grow. If it's stable, it will just decay and go back to a random distribution of stars. So that means that these can grow, and then when they're sheared out, these become spiral arms. So why is this then a problem? Well, it was identified that you can shear these dense features, but if this process continues, then you end up with spirals that become more and more tightly wound. So they start to become more like basically circles rather than spirals, because they could become so tightly wound. And this sort of figure demonstrates how this sort of process occurs. And we don't see spiral galaxies that have spiral arms that sort of are really tightly wound. And it's also perhaps difficult to get, say, a two-armed spiral like the one on the left in this figure, because if you're just relying on sort of random perturbations in the stars, how would you get like two arms lined up? So there's sort of there's kind of two main solutions to this problem, I would say. And one is that instead of having like a spiral arm that just starts like this and winds up over time, you don't just have a constant spiral arm. You have like a spiral arm that forms, and then it sort of disperses or disappears again, and then you get a new spiral arm forming later. So it doesn't matter if it's winding up, because it's not going to last indefinitely. So, and then I'll just go to the bottom, but the other solution is that rather than the arms winding up, you have spiral arms which are just fixed. They don't change shape at all. So then so I suppose the way why you have differential rotation, not solid body rotation, is the galaxy is not a solid body. It's just made up of stars and gas. So if the spiral arms are fixed, then that means the gas and the stars pass through them, rather than the spiral arms just being a system of stars that stay in the arm and get sheared out. I mean, you can have something in between these scenarios. So you can get spiral arms that sort of don't last indefinitely, but are longer lived than just stars that get sheared out. So the spiral arms can be more rigid, if you like, so that they stay together for longer. And so to get something that's a spiral arm that stays together for longer, or a spiral arm that's rigid and fixed, so it just stays the same shape over time, that might occur if you've got stronger gravity. So generally, if you've got stronger gravity in your disk, you can get spiral arms that are more sort of fixed over time and less likely to disperse. If the gravity is strong enough, you then tend to get a barred spiral. And so sometimes we talk about density waves. So I suppose I just perhaps define them as anything where the arm is sort of survives longer than just simply being sheared out as the galaxy rotates. So that can include spiral arms which are rigidly rotating, And spiral arms which are rigidly rotating is usually referred to as density wave theory. It's not often that well known, or sort of perhaps not necessarily so well known that there is a rough estimate for how many spiral arms you get in a galaxy. And there's this formula here that's sort of fairly similar to the Tumoro parameter I showed earlier, and I think sort of derives from the same sort of set of equations, which gives a very rough estimate for how many spiral arms you get. Here's same parameters, the kappa. This is again to do with the sort of rotation of the galaxy. R is galactic radius, and this sigma is surface density. So as you go to higher surface densities, you get fewer spiral arms. And we tend to associate these longer lived spiral and the density waves with, let's say, two 3-armed spirals. And you also see it depends on R. So you sometimes do find that galaxies do look more like what we call grand designs, so perhaps 2 symmetric spiral arms in the center and more spiral arms at the outer edges. So I haven't yet mentioned anything about companion galaxies. So so far, basically these equations, I haven't mentioned anything apart from the stars in the disk. So that the halo does come in through the rotation through the kappa, and in fact is through observations of the rotation that we know that dark matter exists. But otherwise, the halo isn't particularly present in what I've said so far. It doesn't have a big influence. So really, it's more just to do with the stellar disk itself, but the halo does come in through this kappa parameter. But this surface density is just to do with the stars. But there are other things that might influence the galactic disk, things that have a large mass that will exhibit a gravitational force. So bars in the center of the galaxy, companion galaxies, and a sort of more exotic one, which I won't really say anything much about. People have suggested that if you have an asymmetric dark matter halo, then that could influence spiral arms as well. So for the Milky Way, for example, that has a fairly strong bar, and it's being orbited by a large Magellanic Cloud. So I don't think the Milky Way is sort of, I would say, fairly complex in terms of it's got a number of things influencing the spiral arms. So here's some sort of examples of what different sort of spiral galaxies or sort of spirals you can produce, and they may not fall quite neatly into the sort of categories I've described. But what you can, if you have a galaxy where there's almost no structure in the stars, then it's only in the gas that you get gravitational instabilities. And this leads to what we'd call flocculent spiral patterns. So it's all like really bitty. It's just short little transient sections of spiral arms. The gas, I suppose in the gas, well, perhaps this is just like redshift 0. If you're looking at very high redshift galaxies, it may well be different, but at least at redshift 0, where the galaxies, most of the mass is in the stars, there'll be less mass in the gas, and the gravitational dynamics are just such that the gas has relatively low mass, and you just get all these short spiral arms that just come and go. So yeah, on the left, this this is a galaxy that may be something like this. It doesn't show, so the sort of this yellow color is the star, so it doesn't show much structure, but quite a lot of structure in the dust and gas. This is a numerical simulation, so there's no stars here. The stars, if it was shown, would just be well, it wouldn't necessarily be, it would be a symmetric disk. So there might be some radial variation, it might be denser in the center and less dense out here, but there'll be no spiral arms at all in the stars. This is numerical simulation where the stars are just sort of not one uniform but radial varying disk. And so this just shows the gas. And then this is a simulation by a former student of mine. It's showing the stars on the left and the gas on the right. It sort of starts off where the scenario we've got sort of transient but more longer spiral arms than in the previous case. So this is where there is instability in the stars. So the stars are producing spiral arms. And yeah, to begin with, the spiral arms, they're sort of not that long lived, but this one does eventually become, so by this point, it's got a quite clear bar. I'll go backwards so I can play again. It does develop into like a two-armed spiral with a bar, because I assume in this particular model the mass of stars in the disk is sufficient, that it's sufficiently gravitational and stable to develop into a bar. In all these cases, the stars are always much more so much broader than the gas. So the gas always produces these very sharp features compared with the stars, and that's true in observations as well. What your eye is drawn to is the newly formed stars in the gas, and the old stars are like if you just showed them, they'd be like a much broader spiral arms than just this sort of narrow bit, say, along here. This is an example of a bar-induced, well, what could well be a bar-induced spiral. A galaxy with a very strong bar. This is a numerical simulation. There's no spiral arms in this simulation, so they've just modeled a bar and it's produced sort of spiral arms, a bit like the galaxy that they're trying to model. So in terms of sort of two-armed spirals, so I'll talk about M51. So M74 is kind of a bit of an anomaly, if you like, in that it's a two-armed unbarred spiral. It doesn't seem to have a companion or a bar, so it's difficult to explain without sort of invoking density wave theory, where you have a fixed or rigid spiral arms. This is just a simulation with fixed spiral arms. There's no stars in this. It's just a gas disk. It's in the rotating frame of the potential, so the spiral arms are just staying in the same place. But in this rotating frame, you can see that the gas is flowing into the spiral arms, and then it's flowing out again. So the sort of the shape of the gas as it flows out is again due to differential rotation. So it's just the shape that's produced by the sort of gas going around faster in the center compared with the outside. And in this particular simulation, blue and yellow highlights dense molecular clouds, which is where stars are forming in the simulation. So onto Whirlpool Galaxy. So we know the Whirlpool Galaxy is interacting with a companion galaxy, and we think the spiral structure is due to this. So we did a simulation of the orbits of the two galaxies. There has been previous works by other groups I guess we just sort of improved on some previous simulations. We needed to, in modeling the galaxies, we needed some initial positions and velocities for the galaxies, and so I worked with a collaborator, Christian Tice, and he had done many simple calculations. So these were just n-body calculations with stars and a halo, and a limited, fairly low resolution, to determine some initial positions and velocities, which, when run over time, produce the galaxies as they appear in the present day. So he did very many small simulations to generate some initial conditions that we could use. But then in the simulations I did, I modelled M51 with gas, stars, and a dark matter halo. But I didn't all NGC 5195. The companion is just a point mass, so it's just one mass, if you like, representing the galaxy, which is a bit of a limitation, but it makes the calculations a bit simpler and easier to do. And the NGC 5195 is I think about a third of the mass of M51. So this is our simulation. So this is our M51 galaxy. This white dot is the companion galaxy. So it orbits M51 in our model a couple of times. And in this particular model, the companion galaxy eventually merges with M51. So our prediction is that the two galaxies would eventually merge. So on the next slide, there are some stills. So on the right-hand side, this shows our simulation at what would be the present day, so a time of 300 megayears into the simulation. And the bottom panel shows M51 in the same orientation. This on the left shows what would happen if we just ran our model but didn't include the companion galaxy. So you see that in this case, it doesn't look anything like M51. It doesn't have the two-arm spiral pattern that M51 has. So having a companion is a good way of getting a two-arm spiral galaxy. As I say, the one I showed earlier, M74, is sort of, as I say, a bit of an anomaly that doesn't have an obvious companion. So we kind of, we found quite good agreement with the sort of overall shape of the spiral arms in M51. But what we were kind of quite surprised by was that we actually got some quite detailed features as well, albeit they're not quite in the right place or quite perfect. It's still quite surprising that we produced even detailed features. So, for example, in the real M51, we see these we kind of see a quite clear kink in the spiral arm here. We see that in the simulation as well. As I said, the things like kinks are not things you'd expect if you had a rigid rotating pattern. Although some authors suggest that the center might be more rigid and the sort of outer parts less so. But these are not. This isn't really a very sort of symmetric spiral here, or a particularly clear spiral. Is quite a clear kink. And other things we saw, so these features here, like dark features, that's dust, and that sort of dust and gas that gets sheared in between the arms. Here at B, we see quite a long feature going across here, and we see a similar sort of feature here in the simulation. We see quite a lot of gas sort of being sheared off in the interarm region here. We see similar in the simulation. And also in the observations, we see this sort of like stream of, it's a bit difficult to see because you can kind of see it in front of the companion because you can see it in extinction, but you can see this stream of gas up here. And we see the same thing in our simulation here at D. So that was what it looks like in the gas. Here's what it looks like in the stars. So again, when you look in the stars, at least in the old stars, not in the sort of the very younger stars, you get much broader spiral arms. So again, we've got a pretty good agreement with what the actual M51 looks like. I suppose it's a bit different in that our spiral arm sort of seems to more or less extend to the companion, which doesn't seem to be the case here. But it's a quite good agreement with the pattern. So is the pattern in M51 fixed? Well, we found it didn't seem to be fixed in the simulation. So this is a plot of pattern speed versus radius. And if it was fixed, this would just be constant. So it's sort of a bit radially varying. So that sort of suggests that it is slowly winding up. And I did further simulations where I adjusted the orbit so that the companion galaxy just flies past M51. And in this case, you still get a two-arm spiral pattern, maybe not quite as clear. And it persists for hundreds of mega years after the sort of companion galaxy has passed, and sort of slowly winds up over time. So some sort of disadvantages and advantages for different mechanisms. So the tomb ray instabilities, which I've just used to refer to sort of gravitational instabilities in the stars and or gas. So they produce spiral arms fairly readily. There are many numerical simulations which show them producing spiral arms. They don't. Sometimes they're quite transient, but sometimes they do last longer, and that's probably sort of due to gravity. That's allowing them to last for a few rotations. Density wave theory, that can produce these sort of nice grand design galaxies that we see, but I didn't show any numerical examples that produce density wave theory because it's very difficult to produce them in numerical simulations. You seem to require quite a precise set of conditions where you get two spiral arms, but you don't develop a bar instability. Companion, that's what I showed with my M51 example, which produces two-arm grand design galaxy, but not all galaxies have obvious companions. Then the bar. So bars are pretty common in galaxies, but unless you've got a very strong bar, then it's maybe not going to have that much influence on the rest of the disk. And then the asymmetric halo is more an exotic thing, but it's very difficult to measure or observe to see what influence that has. So on just the last part, I was just going to talk a little bit about star formation in spiral arms. So I suppose one of the questions that we're often interested in is, do spiral arms affect star formation? So we know that stars form in spiral arms, but do they actually have any influence on star formation? And we think the answer is probably not. So at least in my work, and I think sort of general consensus from other work is that the spiral arms just gather material together. They just gather the gas together. If you didn't have the spiral arms, the gas would still be star forming. It would just be spread much more around the disk rather than the spiral arms. So this is sort of examples of work I've done. So I ran a galaxy with an imposed spiral pattern. And here's one with no imposed spiral. So this is just like the one I showed earlier where there was only structure in the gas and nothing in the stars. And here's the star formation rate per unit area. The different colors are just different star formation efficiencies. So in these large galaxy simulations, you can't model individual stars. So when you form you convert dense gas into stars, and you do that with some efficiency. So the red is 5% and the blue is 10%. And there, with spiral arms, there is slightly more star formation, but it's not a big factor. So it's sort of maybe a factor of 2. And given the spread for sort of for galaxies that are say the same density or same mass, that's relatively small. And we also can see it in other measures. So this is work by a former student who was modeling interacting galaxies, looking at molecular clouds, dense clouds where stars form, and on the right showing the properties of these clouds. So that's mass, that's velocity dispersion, and this is how gravitationally bound they are, so how gravitation dominated. And in all these cases, I say that when you have the perturbation, you do tend to get some slightly more massive clouds, but otherwise the properties are really similar, whether or not you've got a 2-armed spiral that's produced by a companion, or just a sort of a multi-armed transient spiral arms. Doesn't seem to make very much difference. And so that was with simulations, and the same thing sort of found in observations as well. So this was work on Fang's survey of galaxy. So people take their galaxies, they make or masks to identify different regions, like spiral arms, bars, interarm regions. And here, so on the right, this plot shows a star formation rate per unit area versus the radius in the galaxy. And this was taken over kiloparsec areas. So some were in spiral arms, some were in interarm regions, bars and centers. And the interarm, so which are grey, and the spiral blue aren't really that much different, and the disk generally. The way you do see bigger difference is the center. Actually, the bar's quite different as well. So you do see differences, but the biggest differences are with the center of the galaxy rather than the spiral arm making much difference. We've seen the same thing in the Milky Way as well. And then just lastly, I'll just highlight sort of work that we're doing on slightly smaller scales. So recently we have sort of new JWST images of spiral galaxies, and here we have M51 in a collaboration that I'm involved with. So the colors here, so this shows dust, and the sort of dark orange is sort of colder dust, and these bright white and yellow bits is dust that's hot and being radiated by stars. So in some places, so you kind of see the structure, and we're seeing this a lot with JWST, and we see it in the HST images as well. You see clusters, and then round them you see these bubbles or shells, and all these bright regions where the gas is being irradiated. And this is a pretty big one, but you can see smaller ones as well. And so these are sort of bubbles that are produced by feedback, by ionization and supernovae. And the observations, like these JWST observations, indicate that the time scale for this to happen, I mean, this is probably quite big one, so this would take longer, but the time scale to produce these sort of little bubbles with around the clusters is pretty short, so only a few mega years or so. So we've been looking at this with simulations just to explain what the feedback processes are, or what we call feedback. And two of the main ones are ionization, so H2 regions. So you get ionization, which produces H-alpha emission from the ionized hydrogen. And you can see in all these spectacular images of star formation, that's what you're seeing, the H-alpha emission. And this ionization heats the gas up to 10 to the 4K. So hot, it's hot, low density gas. So this occurs for any time you've got massive stars. And then once the massive stars reach the end of their life, they undergo supernovae. And if you look at the LMC, for example, you see all these shells and holes and things, which we think are due to lots of supernovae occurring. So we've been modeling these in simulations. So what we've been doing is taking initial conditions from galaxy scale simulations, re-simulating them at much higher resolution to follow the formation of clusters and to follow these ionization and supernova processes. And in these simulations that I show, the dots represent small groups of stars. So here's sort of an example. This is a section taken from a spiral arm. So the spiral arm just goes along here. So it's only a very small section of a galaxy. It's 60 parsecs. And it just run for, well, we run it for about 20 mega years or so, but just shown here is about 12 mega years. And so this is like a cluster of stars, or it's like an OB association. So these are kind of quite loosely grouped together stars, so a loose sort of cluster of stars. And in here, these stars include massive stars, and here this is a supernova that's blowing out the gas. And so initially, yeah, all the green and blue is gas, but as you see over time, lots of this gas gets dispersed. And you just get sort of dense features just sort of at the top and the bottom from the remaining gas. And we see this happens on fairly short time scales. Just to show in this video, this shows the ionization itself. So this blue, this sort of colors here, these are sort of, this is where you've got clusters, and the massive stars in these clusters are producing all this ionization here. And if I go on to this slide, then here this shows with ionization and supernova, and this is without ionization or supernovae. So here, all this sort of part here is low density that's been ionized. And you've got these sort of, this is an OB association here and here. Without the ionization, you've got these very tight, very dense clusters of stars, and these are still all associated with lots of gas. And we compared our simulation here with a very famous Orion region. So on the left is an observational plot of Orion. So this is like the whole Orion region, hence it's sort of about 100 parsecs across this figure. And this is from our simulation. So we kind of see similar sort of size cluster of stars, and similar number, similar mass. We see like a similar number of groups. So we see about 4 groups here and about 4 or 5 groups in the real Orion. Yeah, so we ran a number of simulations. So some of them just produced like sort of 1 or 2 big clusters, but this one was characterized by a relatively low initial gas density and quite large velocity dispersions. There's quite large dynamics in the velocities. And just to finish, we've also been putting our clusters into synthetic observations. So we take stars from the Gaia catalogue. What we've basically done is combined our simulated cluster with Gaia stars, and then produced a combined catalogue. So this just shows some images that we made. So if you would be able to see our simulations with an optical telescope. So the red is the gas, And then this is real stars and our cluster stars. So, and different types of clusters that we've got. So Orion type cluster and a Westland 2 type cluster. So Orion 1, you can see it at younger times. These sort of, you can see here the sort of the brighter, bigger stars, and you can clearly see the gas. Westland 2 is a really massive cluster. So our model that was a bit like Westland 2, you can see really easily. This is at different distances as well. So a lot of the work we do in star formation in the Milky Way is really just in the sort of closest kiloparsec or so. But if you're looking at something like these massive clusters are much less frequent, but you can still see these at quite big distances, whereas something like Orion, which is only at 500 parsec, would be quite difficult to see, particularly as it gets older at larger distances. Yeah, I think that's I was going to finish there. So just at the summary, so spiral arms can form readily in disk galaxies, but I suppose that the quick question is how to maintain ongoing spiral patterns that resemble observed galaxies. So spiral arms could be transient. They could be sort of more fixed by or they could be more rigid structures that are still transient but last many rotation periods, or they could be sort of fixed over a very long time scale. And so in the latter, that would be density wave theory, is something called density wave theory. And we see in the galaxies that we see some where it's quite likely that they're just sort of transient arms, and we see some like the Whirlpool Galaxy where we think that where it's fairly clear that the spiral arms have been induced by a companion, and this is producing a 2-arm spiral structure. But other galaxies might be more complicated. So the Milky Way, I think we're kind of coming to the conclusion there that that's transient, probably transient spiral arms rather than a sort of like a fixed density wave. But it's more complicated by the presence of the bar and the LMC. We don't think that spiral arms actually have much influence on star formation, albeit that they're where stars form. And we currently sort of, at least I'm involved with projects with JWST to help tell us more about star formation. And we're sort of interested in the timescale for star formation, timescale for when clusters are no longer embedded in gas. So when they separate from the gas that they form in, how long that takes, and the properties like the mass distribution, the ages, and that we can get from clusters in galaxies like M51. So thank you.
Thank you very much, Claire. That was fascinating. Any questions for anybody? Yep, Tony. Sorry, you want to? Yeah, there's a spare one here. I'll pass it round. It's a good exercise. Yeah.
Can you hear me?
Yes.
In the equations that you showed, where is the effect of dark matter?
So as I mentioned, the dark matter, when I was saying about what produces the spiral arm, the dark matter, it comes into the rotation. So it was a kappa parameter. So it just depends on, well, so Toomey developed equations for the gas and stars, or you can have one that takes into account both the gas and stars combined. So that just needs the mass of the gas and or stars, and the velocity dispersion, which is just the random motion of but then the rotation or the shear is directly due to the dark matter.
Anybody else got a question? Sorry, yeah.
Claire, in terms of the model of M51, how well does the observed age of M51 correlate with the point in your model where the patterns match?
I mean that was kind of put in by design, in that the conditions that we used had already been shown to match the position of M51 at the current time.
Okay. Yeah, okay, because we effectively, with observation, we're looking at a snapshot, and you're running through many mega years of models to get to an image which looks the same. So is that kind of, how much of that is driven towards what you're looking for, rather than taking a model, predicting something and finding that's what you've got?
So in that case, it was just trying to reproduce M51 as it is now. And so, as I said, I took someone else's work, or a collaborator who had done this already, but they just run much simpler models. So they didn't. They didn't necessarily, or they just run very low resolution. They didn't include gas. So they wouldn't have necessarily got the spiral pattern out. They'd have just got the positions of the galaxies.
Okay, thanks.
Thank you. Anybody else got questions?
Do your simulations show? Cheers, Colin. Do your simulations show that AGN have an active effect on the spiral arms? And if so, does it make a difference if they are actively accreting? Did I get that run right way?
No, there's no AGN at all in this simulation. So, I mean, for M51, I think that is a safer galaxy. So it does have AGN activity, but that's not included in the simulation. So I don't think it have an impact on the spiral arms. It might have impact at the galactic center, which we've not included. But no, it's not included in the simulations.
Thank you. Any more questions on them? Thanks. Great. Well, Claire, thank you very much. Thank you very much for bearing with us through changes of times, and also for getting to send you the Zoom link. So thank you very much indeed. Much appreciated. Really good talk. I thoroughly enjoyed it. And I think the questions, I think people did as well. So thank you very much.